now that my diatribe's over, right? So I'll kind of give you an idea of what we're doing here. So I'm thinking about things like this, right? So I've got two different groups. Each of them have a sample mean. I got to switch this because, of course, they wipe these computers every day. So I've got two different groups. I've got a sample mean from each one. Right? So I could look at the difference between those sample means. Before, we only had like one group, right? We were focused on like the average starting salary of doctors. Well, now I'm looking at maybe the average starting salary of doctors, the difference between that and the average starting salary of lawyers. Okay? So I can almost think about it as I've almost got like this difference variable, and I've got this sample difference, right? I can't observe what the true difference in salaries for those two groups is, but I can look at the difference between my two samples from those groups. What ends up being true is just like we had our sample means being normally distributed. Is something wrong? I couldn't hear it. Is it, can you hear me now? Is it, here, let's see.
It's okay, I just know what it is now.
No.
I can live with it. I was very.
So what? You still hear it?
I don't think it was the marker.
Oh, okay. I think I've got it turned all the way down now. I was seeing the looks and I was like, wait, I changed the mirror. Okay. We're okay now? All right. So just like with our sample mean was normally distributed around the true population mean. Our sample difference that we see will be normally distributed around whatever that true difference is. But now for us, we can't observe that. So just like before, we're going to start having things like assumed true differences. So really, it's almost just like the notation has changed a little bit. All the same principles apply, right? It's just now a little bit more work because now we have two groups. We have to calculate the sample mean from each group and then find the difference. But it follows a normal distribution. All the same sort of stuff is going to apply, right? Whatever our sample difference is, we can think about, I could probably turn that into a Z statistic, right? And it's not going to look a whole lot different than what we were doing before. It's just we have a few more moving parts now. Questions on that? Is that kind of making sense? And we could do it with two groups sample proportions, right? Kind of thinking about the sample difference between two groups proportions, it would follow the exact same set of rules. Okay. So now let's go here. Let's make sure this switches over. Oh. So we've got three different situations. The difference in sample means when we know the population variance, the difference in sample means when we're looking at proportions, and the difference in sample means when we only have sample variances or we don't know the population variance. We can do confidence intervals for each one. We can do hypothesis testing for each one. And then I think this last one, I kind of grouped them all together, but I don't think we're gonna have enough time or the time I want to give to it for next Wednesday. So we'll save matched pairs for kind of after the exam. So we're just gonna be looking at confidence intervals, hypothesis testing, and we're looking at these differences now between groups. But it's kind of like the same three types of examples that we had with one population. Okay. So I've got some motivating examples. I'll go through them quick and then we'll actually work through them. But maybe I've got econ and theater alum. I have their starting salaries, and I want to build a 95% confidence interval for what the true difference in their starting salary is. Right. So based off the samples, I think here I've got 45 and 33. So I see a $12,000 difference, but it could be. I'll try to give some insight. It could be the case that, right, I just so happen to see a difference way out here of 12,000, even though the true difference actually is zero, right? So even if the true difference was zero, there is still some positive probability that I see something out here in the tail. So I can use what I know about the normal distribution to then build different confidence levels, right, for whether or not the true difference is zero, right? Basically, I'll build my confidence interval, and if zero is not in that confidence interval, I could say, well, then the true difference is positive. If 0 is one of the values in my confidence interval, well, what that's telling me, so let's say I build my confidence interval around 12,000, and let's say I see, I don't know, 36 and -12, right? So I think that should be centered around that sample difference I found of 12,000. Well, if 0 is one of the possible values in that confidence interval, then with whatever level of confidence this was, I can't say that the true difference is anything other than 0, even though the sample evidence I found was in fact positive 12,000. Right? I found that there was a difference, but if the variance on this distribution is really, really wide, well, it's highly possible that I saw a sample difference of 12,000, even though the true difference is in fact 0. So that's kind of a little bit of a roadmap of where we're going. So the other one we can think about, I've got that survey, I think I've already used this for an example, where it had people, asking people about the Affordable Care Act, and it had their changes in attitude over time. All right, so going from 2010 to 2011. I then have an example where I want to test for what's the confidence interval for the true difference between response time for non-texters and people who are kind of using their phone or Siri or kind of texting while they're driving. Okay. So those are our kind of our setup. So what we know about each population, right? We're looking at the difference between two different populations, like econ theater majors. We'll start out there. Well, those econ majors, their sample means will be normally distributed around their population mean. We'll call that group 1. They'll have their own population variance, right? So if we take a sample, we know that those sample means from group 1 will be normally distributed around that group's population mean. Okay. Same kind of thing holds for group 2. It's just that they're going to be different values, right? So what ends up being true is the true difference, right, between the population means. That's what our sample difference will be centered around. Okay. And then the variance, or I should say here, the standard deviation of the difference in those sample means is going to look like this. So we've got the equations here, but I'm going to kind of give you context for why they are what they are. Okay. So, and I'll show those again, and they'll end up being on here. So if I think about what I had before, so here was my confidence interval equation before, where this guy here represented the standard deviation of my sample means, right? Well, now the statistic that I'm looking at is going to be the difference in sample means. I'm going to still need to go out a certain number of standard deviations such that there's alpha over 2 on either side of my confidence interval. But now here, I need the standard deviation of the difference in my sample means. So I had the equation up there on the slide, but I think it makes more sense to first think about the variance. So the variance for the difference in my sample means is simply going to be the sum of the variance for each one of these sample means. So the variance for the first sample mean will just be the variance of the data I'm sampling from over my sample size for that group. The second group's sample mean will have a variance of, well, whatever the original variance was on the data I sampled from that group divided by the sample size I have for that group. So the variance of the difference in those sample means is just add the variance up from each one of those sample means. Now, we wanted the standard deviation. So what did we have to do? Well, to get rid of this, we then took the square root. Right? And so that's what was up there in the slide. Right? So really that just comes from the variance for the difference in two sample statistics is just the sum of the variance of each statistic. Okay? Now, once we have the standard deviation for the difference in those sample means, now it's just a matter of plugging that in up here. And we've got, if you can't ever see anything using this, let me know. It's hard for me to know exactly how large it's being displayed to you. So if you need me to zoom in or anything, let me know. Or have a question about something I wrote down. So we've got our confidence interval. It's, there's more moving parts. It's going to take a little more time. We just have more values to plug in. But in the examples, like for the upcoming exam, you'll be given the two sample means. You'll be given the known population variances. You'll be given the sample sizes. It's just a matter of plugging our values into that equation and then kind of using that skill that we've already been using for confidence intervals, which is looking up that Z value that gives you the area you want in the tail, or kind of that inverse process, right? You've got the area you want in the tail, find that value in the middle of that Z table, and then find the corresponding Z score that gives you that. Okay. Any questions on that so far? We'll work through some examples here. So keep going here. I couldn't fit this all in one line, so that's annoying, but at least I showed it to you up there on the screen before. But right, we can kind of line this up with exactly what we're doing with one population. Okay? So the steps are going to look exactly the same as what we were doing before. It's just notice we have two of everything now, basically. Okay. So let's try to work through this problem that I showed you earlier. So we've got two groups, econ majors, theater majors. The econ majors have a starting salary of $45,000, theater majors, $33,000. And I'll switch to this. I'm just going to kind of write along here as we're working on, or as I'm kind of reading through this. So we've got the sample mean for econ is 45,000. Sample mean for theater majors was 33,000. We've got our sample size was what, 40 econ majors. Theater majors, we had 50. What should our alpha be here? Yeah, the percent outside the confidence interval is 5%, and decimal form is 0.05. And we have known population variances. I guess this is kind of out of order for each of these groups. So what was that? 9,000. And these are variances, right? Not standard deviations. Yeah, variances of 6,000 here for the theater majors. So all I've done so far is write down everything that I know. Okay. So all I've done is write down everything that I know, and now I've got everything kind of centered or all in the same place right here. Now it's just a matter of plugging these in. I mean, I can walk through this and I could write it out, but it's really, at this point, it's not too difficult. I've got my group one was econ majors. My group two is theater majors. So that sample difference that I'm finding is going to be kind of skipping a step here, but right, my sample difference, or the difference between these two sample means, is just 12,000. So my confidence interval will be centered around that value. Okay. And then can plug everything in over here, right? I've got my two population variances. So 9,000 divided by my sample size of 40, and 6,000 for the other group divided by, I had 50 theater majors. Now, in practice, especially like for the in-person exam on your calculator, calculate this kind of ahead of time, like do the intermediate step. I think that will make it a lot easier. So find that standard deviation so you can just plug in one value instead of doing like all of this at once. Now, the only thing left to do is find the Z-score. That gives me what? 0.05 over 2 in the tail. So 0.025. So let's go pull open my Z table. There it is. So let me hide this. We had 0.025. So I'm going to hunt for that value in the middle here. It looks like, oh, it's right there exactly. So negative 1.96, right? But I remember that for my confidence interval, it's already built into my equation. So all I need to do there is plug in that 1.96, add this margin of error to get my upper bound, subtract that margin of error to get my lower bound. Okay. So these two population confidence interval ones, honestly, it's mainly computation, right? Other than kind of making sure you know how to look up those Z values. But hopefully we're getting pretty comfortable with that from all the other confidence interval questions that we've looked at. Okay. Any questions on this one? Okay with this? Doesn't seem too crazy, right? It's like stuff we've already done, just like a little bit more. So Oh, I didn't mean to do that. I want to go to share screen. I'm out of practice from how to do this stuff. So got kind of everything here. Right? We identified all the information we were given, figured out what alpha was, found the z-score for alpha over 2. Then it's just a matter of plugging everything in. So I get a pretty narrow confidence interval here, which is nice. You know, I think here it's because my sample size from both groups, you kind of think about my total sample size is like 90. So I'm starting to get a pretty high sample size. Also, I find these variances are actually pretty low. I made these numbers up because this is the problem with these examples where you have a known population variance. Well, if I don't know what the population mean is, how am I supposed to find the population variance, right? So I was trying to think of a fun example. So I ended up choosing kind of variances that were a little bit too low. And I shouldn't say they're too low. It's just that we've got a really tight range of values here, right? I mean, especially when we're talking about the difference in salaries. So here, with 95% certainty, I can say the true difference is somewhere in this range, which means I can definitely rule out that there's no difference, right? No difference would be a value of 0. 0 is nowhere close to being in my confidence. Right? In fact, if you told me, no, everyone makes a big deal. I don't think there's a big difference in theater and kind of econ majors starting salaries. I think it's something less than 10,000. You could actually tell them with 95% confidence, no, it's not. Right? Not to pick on theater majors. I mean, if you look at the data, it's just lower, right? Any questions here? All right. I'm probably just jealous that I'm not. So I had this other example. And I think we'll work through it a little bit. I'll go through it pretty quick. So we've got Ohio and Indiana. We're looking at 24 different years, and we're looking at robbery rates, right? So we want to say, with 95% confidence, what's the difference between Indiana and Ohio rates? So this is one thing. It's important to make sure that you're doing the order correctly, right? So when I'm looking here, Indiana had a crime rate of 109 per 100,000 people, and then Ohio is 163 per 100,000. So they're in the same units per 100,000. So we can just use the values here. We've got these known population variances. We've got 24 years for each state. So our sample sizes will be both 24. Okay. So I write down everything that I was given. Right? Is that kind of clear there? My alpha, 95% level, is 95%. Sorry, for the 95% level, my alpha would be 0.05. Right? If I look up 0.05, what will the z-score be? Should be easy to remember. We just looked it up. Right? It's going to be the exact same thing. Every time I'm looking at these same values for alpha, I'm going to find the same corresponding z-score. So anytime I want to build a 95% confidence interval from the standard normal distribution, I'm always going to find that value of 1.96 from my table. Right? Is that clear there? What I'm saying? Okay. So we look it up, we get that same thing on the previous problem, right? It's the same level of confidence. From here, it's just a matter of getting everything plugged in. I mean, I don't want to spend too much time on these because really it is computation. On the exam, I'll probably focus less on I'm not going to give you a confidence interval question from each one of these possible 2 population examples. I get whether we're going to be kind of rushing through this 2 population stuff a little bit. So when it comes to the 2 population stuff, I'll probably focus more on the hypothesis testing. Because really the hypothesis testing, being a 2 population example, doesn't really change much. The only thing it changes is that z statistic. Okay. So I've got this range of -64 to -43. So I can say with 95% confidence, the true difference in Indiana and Ohio, what were they? Crime rates or murder rates or something? I forget now. Robbery rates, there you go. So the true difference is somewhere in between those values, which means I could say that the true difference is negative. So what would that imply? Right? If I've got the differences between Indiana and Ohio, with 95% confidence, I could say what? Yeah, that Ohio's not a good place to live, right? But no, right? They have much higher robbery rates. Now, this is per 100,000 people. So we kind of already kind of controlled for the per capita here. So it's kind of interesting to see that those robbery rates are that much different. Okay. Questions on that? No, I'm going through it kind of quick, but I want to be able to kind of cap this off today. So we at least kind of get through these examples where we have known population variances. So now let's do hypothesis testing. So this is like the freshest stuff. This is probably going to be some of the, I think it's tougher on the main exam. I think hypothesis testing is the most difficult topic. All right, if we just call the difference between these sample means I kind of had D hat there, right? Like that represented the sample difference. Well, then the true difference, we would kind of just use the notation of this as capital D. So what we're going to do is come up with an assumed true value for that difference. So we've got an assumed true difference. We have our sample difference. This is going to look no different. That was not intended. It's not going to be any different than what we were doing before. Right? So let me try to give you an insight as behind. Maybe we could build and probably figure out now what that test statistic is going to look like. Okay? So if I've got, this was my test statistic before. And this was, call this our Z statistic, right? So the way that we come up with these Z statistics or Z values, we take the statistic we're interested in, right? The sample value that we found. So if we're going to try to do a Z statistic for this sample difference, we're going to take the sample difference we found, which in practice, right, we calculate by taking the two sample means and subtracting it, like finding that difference. We'll then subtract the assumed true difference here. So we'll subtract some assumed true difference value and then divide by, instead of the standard deviation of our sample mean, it's going to be the standard deviation of the difference in our sample means, which for confidence intervals we said was just the square root of kind of each sample means variance, which the variance of each sample mean would just be take the population variance of the data you sampled from, divided by that group's sample size. Okay. So just from the things we've talked about, we just kind of went through, this should be the Z statistic formula when we're looking at the difference in sample means. Any questions on that? So I'm trying to like reiterate and show you that there's a pattern, right? You're taking the statistic you're interested in, subtracting the assumed true value, dividing by the standard deviation. Now, those standard deviations have slightly different formulas sometimes, but the process of what you're doing is really the same. Okay? I'm going to make things easier for us. Okay? We don't have to do this. And maybe after the exam, we'll do some match pair stuff. I'll show you like this doesn't always have to be 0. But I'm going to give you the null alternative hypothesis that we're using for two population examples that assume true difference. We will always use 0. Okay? And I'm going to test it against any other value. And this really makes sense because if I'm thinking about null and alternative hypothesis for this true difference, so I've got like this true difference, I might say, well, I want to test to see is it greater than 0, which really would imply, right? This would imply that, if I just move things around here a little bit, seeing a positive difference would imply that group 1 has a higher sample mean than group 2. So, I'm looking at that kind of the difference being greater than 0. I rewrite it this way. I rearrange it. What that's really saying is group 1 has a higher mean than group 2. If I'm thinking about less than 0, what that's really saying is then group 1 is less than 2, right? If I see a negative difference, right, that difference is less than 0, then I'd be thinking about group 1 has a smaller mean than 2. And the one that we'll kind of see most often, and actually you'll probably see it in some of your upper level courses, is you assume it's equal to 0, right? Which is really saying I'm wanting to test to see whether or not group 1 and 2 are any different. Right? I just realized here I'm using sample means. I should be using the true population mean values here. But in practice, what we're going to be looking at are the sample means. So I'm just trying to give you some insight as to why that 0 is interesting. It might sound like I'm really restricting this, but no. I mean, quite often we want to know did I see sales be any different before or after this advertisement? Did I see, the average quality in my product change before or after some change I made to the production line? Right? So we'll always use that assumed true value of 0. So that'll make life a little bit easier, right? We'll have the same kind of thing, left, right, and two-tailed tests. So we got our one-sided, two-sided test. Just now we're looking at that true difference. And we kind of already talked about, where is it? I'll come back to this. Oh, there it is. We pieced together what that test statistic equation would be. Right? Now, all these slides that I skipped through right here, these are really just you've already seen these. These are exactly what I showed you the first time we had hypothesis testing, right? So we still have the exact same steps. It's just that calculating that test statistic will be a little bit different, a little slightly different equation, right? We're still going to compare the p-value to alpha. I'll move. There we go. It's still going to be for a left tail test, the p-value is the area in the left. Right tail test, p-value is the area to the right of your test statistic. Two-tailed test, you find the area that's in one tail and multiply it by 2. Right? And we still compare it to alpha. So nothing's really changed there. We're still using the standard normal distribution when we have known population variances. So for our left and our right in our two-tailed test, we're going to find the exact same critical values we were before as well. So the p-value critical value approach doesn't change at all. The only thing that changes is how we calculate that test statistic. All right, so let's try to work through an example here, because I think just working through these is always a little bit more helpful than talking about them. So you might want to test for whether or not tropical storms have increased, and they should be releasing their next batch of data soon, so it'll be interesting to get the most recent. But you can kind of see here, I forget, some weather service had this, the number of tropical storms across the globe. From 1990 to 2011, it was 22 years. So we had about 15.5 was the average number of storms in the Atlantic Ocean. Right? And in an older time period where we had 32 years, the average was 9.7. So this is my sample, right? These are the ones I observed. Like maybe there was some that I couldn't observe here or some that I couldn't observe there. Also, there's more tropical storms across the globe, not just in the Atlantic. So this is like my sample. We're going to treat this as a sample. So I've got 15.5 and 9.7. So my sample difference, if I'm writing this out, I'm looking at group 1 is my newer time period. Anytime you have time period examples, like where you're looking for the change across time, you're always putting the newest year first. That's just the way that we kind of talk, right? We would say tropical storms have increased if I see a positive difference there. We'd say they've decreased if I see a negative difference. So we're thinking about looking for this difference in our sample means, right? We're going to put, think about it as like the newer time period minus the older time period. So if I want to test for whether or not tropical storms have increased, what am I thinking about that difference being? So if I'm thinking about the true difference, and I want to test for whether or not it's increased, yeah, right? If they've increased, then this difference, the newer, the number of tropical storms in recent years would be greater than older years, so the difference should be positive. So that's what I want to test for. So that's my alternative hypothesis. Also, if you were choosing from this list up here, which one should you definitely have chosen? I told you that we're always going to use an assumed true difference of 0, all right, for the two population examples, okay? So I wasn't trying to, didn't have any other options here that had a 0 in it. So our assumed true difference is 0 here. This is what we want to test for. So we assume the opposite is true. Now I'm writing this out like what the actual difference is, but right, we could just write it as that, kind of using that true population difference kind of notated by D. So I've got this true difference. I've got my null alternative. What type of tailed test do I have here? Yeah, I've got a greater than sign in my alternative hypothesis. So the only evidence that supports the alternative and goes against the null would be evidence on the right. Okay? So I've got this difference between group 1 and 2, right? I know that the difference in those sample means should be normally distributed around whatever that assumed true difference value was, but here I've assumed it's 0. Okay? So the next step would then be, I need to turn the difference I found into a z-value. Well, what was the difference I found? Looks like it was 15.5 minus 9.7. So what? 5.8 was that sample difference I found. I need to turn that into a z-value. Then for a right tail test, I could look that z-value up and find that p-value. Right? So that's kind of mapping out what we're going to be doing here. And I'll blow this up here in a second. So I think the next question, I'm actually going to ask for confidence intervals, right? So we will work through all of this together. So if I want confidence intervals, if I have a right-tailed test, what's something I know that's going to be true about the confidence interval? Sorry, not confidence intervals, critical values right away. If I have a right-tailed test, my critical values, right, they just are z-values. They give me my desired alpha in the tail. So I want the critical value, and I'm going to look. I'm going to show you how we could look up all three. I think I actually specified in the slides which one, but we're going to look up all three. Okay. So I want these critical values, right? And then thinking about for a right-tailed test, my rejection region is the area to the right. What's going to be true about those critical values? They're all going to be positive. Okay? We said right-tailed test, critical values are positive. Left-tailed test, we're on the left side of the distribution. Remember, standard normal distribution is centered around 0. So the right side, positive values, left side, negative values. Two-tailed test, we said we have pairs of critical values, right? We have 2 critical values for a two-tailed test at every alpha level, and then we have kind of alpha over 2 in each tail. So I'm going to use, there we go. I'm going to use the shortcut, which is, I'll just open up a Microsoft. There we go. I'm going to use the t-tables, even though I know I'm supposed to use the standard normal, but I'm going to go to that very last row, because even though these are the student t-tables, they told me the standard normal values in that last row, right, where I have degrees of freedom of infinity. So I wanted the areas of 0.1, 0.05, 0.01. So those are the 3 columns I'm going to look at. That very last row, so 1.282, 1.645, and 2.326. So here, I've got 1.282, 1.645, 2.326. Okay. So I've got my 3 critical values. Now I need to come up with my test statistic. Right? So I'm going to try to figure out what my test statistic is. So I'm going to go my sample difference. I'll write it out so that we can plug our L values. Right, so that's the equation we're going to use. If I go back to the slides, I have my sample means given to me, my sample sizes were given to me, my population variances were given to me. This assumed true value is 0. Okay. So really from here, it's just a matter of plugging everything in. So right, and we found the 5%, but we also found other ones. So we've got critical values. Here, all I'm doing is I've got my 2 sample sizes, population variances, and the actual values of those sample means. So it's just a matter of plugging all those values into that equation. These test statistic problems, hopefully, are the ones that I see you guys get the highest proportion correct. The highest, those should have some of the lowest incorrect responses in the sense that you're really just plugging values into this formula that's going to be right in front of you. Now, in practice, I would maybe find this denominator ahead of time just to like not put it all in one line so you don't mix up any parentheses or anything. But that's really, those test statistic problems I don't think are too bad. So I've got a z statistic of 4.9. If I'm thinking about where does that fall, it's going to be way out here, right? So I could say that I reject at the 10% level, 5% significance level, and the 1% significance level, right? I'm in the rejection region clearly for all 3 of these. Okay? Furthermore, if I'm thinking about the p-value, which would be the area to the right, in fact, I didn't even draw my tail out that far, right? So that p-value would be the area to the right of my test statistic. So here was my test statistic. The area to the right is my p-value. What's that p-value going to be very close to? Basically 0, right? So if my p-value is approximately 0, what levels am I going to reject at? Well, I look at my alphas, 0.1, 0.05, and 0.01, going to be less than all 3, which is the exact same rejection decision that we made using that critical value approach. Okay. So if in fact the true difference was 0, the probability that we actually saw the sample difference between those time periods that we did, or anything even larger, is basically 0. So if the probability of us seeing that is basically 0, it probably means the true difference is probably a lot closer to that sample difference we found. Right? So we're okay rejecting that null, which is that that difference was what, less than or equal to 0. Just making sense. It's kind of like I don't know, hopefully seeing like the application of this. I mean, like I said, I think it's what's the next marketing class? Are there any marketing majors? I forget. What's the class you have to take? I think this is a prerequisite for it. You guys are registering somewhere. You guys know or not? If you don't, it's fine. Yeah. Oh, okay. So I had some previous honors students. I just know marketing specific because they kept coming to my office and asking me for help after they were out of the class. But you basically do a lot of this hypothesis testing. A lot of the times what you hear it called are like t-tests. Now t-tests are when we have sample variances, not known population variances, but it's really the same idea. We'll eventually kind of work through some examples where we only have sample variances. Other than that, we're on time. Yeah, 5 minutes. So let's see. I got some more examples here. We'll work through one more example. So we got our test statistic. We got proportions. I'm gonna come back to proportions only because I think it's easier to make the connection. And I just brought up what happens if we only have sample variances, right? So we'll look at sample variances a little bit here. We'll start with them on Friday, and then kind of finish with the difference in sample proportions on Friday as well. And then hopefully we've kind of covered everything. We'll be able to review a little bit on Monday. I've got those practice exams up there. I don't know if you saw, I put 2 videos up. It doesn't quite line up with the numbers because I'm doing them for my other 2 sections as well as yours, and practice exams look a little bit different. However, they are the exact same questions. So you can see me working through those first 10 problems. I'll try to get some more videos up tomorrow of me working through the rest of them. But what we're going to do when we don't know, how did this go back to? That's frustrating. So what happens when we don't know those population variances, which is more realistic, right? Usually all we have are sample variances. So just like with one population, we're going to have to use those student t distribution, okay? But I mean, we're thinking about the confidence interval. It looks exactly like problems we just worked through. It's just instead of population variances, we put in the sample variances there. And instead of the z value, we have to use the student t value that gives us alpha over 2 on each tail. So that's not wildly different from combining what we did with one population sample variance examples to what we just worked through earlier today, which is the difference in sample means where we knew population variance. The only thing that changes are we're using that student t distribution, and obviously we plug in sample instead of population variances. So we want to mention a little bit more before we get out of here. So it doesn't look that much different, but notice I've got a different symbol for the degrees of freedom in here. It's no longer n-1. So what would n be, right? Well, I've got two sample sizes. So do I add them up and subtract 2, or add them up, subtract 1? What do I do there? The mathematical proof is not as nice on this one. And so what ends up being true is your degrees of freedom. How many degrees of freedom? All of them. Looks something like that. That's nasty, right? So it's going to be some relative ratio of your sample variances and sample sizes from both groups. Now, I'm not going to make you use that formula because I'm nice. And it's just asking you to make a mistake on your calculator. So when it comes to the exam and it comes to these examples that we'll work through in class, I'll give you the assume like what the degrees of freedom is, because these calculations are not very fun to make. Right. So, but really, if you notice, all it is sample variances and sample size from each group. Once you find it, if you don't get an integer, remember that student t distribution, all the values on that left side for degrees of freedom are all integers. So whatever value this equation gives us, we always round it down to the lowest integer. Kind of erring on the side of caution, right? Remember, if we go to a lower degrees of freedom, we see the t values get larger and larger to get whatever desired area we want in the tail. So I'll be giving you this assumed 2 degrees of freedom. We won't have to worry about using this equation. And we'll work through some confidence intervals and hypothesis tests with that, and then look at some proportion examples as well. Okay? Are there any questions for me before I let you guys get out of here? All right. Don't tell too many people that I went on a little rant today, but I really do highly suggest giving the opportunity to make that known, especially on your way out. I would definitely.
You just all need to get rich and you get to know about money.
Yeah, every time